So after having understood the concept of generation of single phase AC sinusoidal, which is like a E equal to Em sine omega t or 2 pi f ban sine theta in general, quantified as a Em sine theta or Em sine omega t by a square or rectangular frame of generator concept, which is a rotating conductor concept. We have learned some definition related to waveforms, like what is a waveform, what do you mean by instantaneous value, what do you mean by a one cycle, frequency, time period, peak value, peak to peak value, like that. And just we have seen one numerical concern to that. We have to revisit such numerical in number almost when we go to the end of this discussion. So after having understood some prerequisites of representation of sinusoidal quantity, it becomes necessary for us to understand further important quantities like representation of an alternating quantity by RMS value, root of mean of sum of squares of instantaneous values. It is also known as effective value. So how we define RMS value of an alternating quantity is the task. Can I define RMS value, effective value, directly? I cannot define it directly. Then how it is defined? RMS value or root of mean of sum of squares of instantaneous value, which we call in short form RMS value, with the help of a definition, a type of sample waveform, its approach we can understand. Let's say a waveform which is shown to you over here, a current waveform which is on the ordinate I have a current, along the abscissa I have time. This is a pattern of a wave, sample wave, any arbitrary wave whose RMS value I am trying to define. Before that, I must know it must be an alternating quantity. It is having a set of positive value, set of negative value, and repetitive in manner. That's called alternating. Such a alternating quantity need not be sinusoidal. I am trying to define arbitrarily first time. Any arbitrary alternating quantity whose RMS value we want to define. To define that, let us consider a representation of a waveform for a certain observation t seconds. You can see on the x-axis of this representation, time is the notation t in second. On the ordinate vertical axis, I have a value current in ampere, and the projected graph is shown to you. This is the sample current I have taken. Then this current is applied to a resistor. Can you see in the top of the corner right side, I have shown small clip rest of a circuit where there is a supply and a known resistor R ohm is there. When a known resistor R, to which this quantity whose RMS value I want to define is connected for a certain amount of time t. It means when I connect a quantity whose RMS value I want to define to a known resistor for a known amount of time. This is my first requirement. Once I connect such a quantity to a known resistor R ohms for a known time t seconds, what is that heat resulted in this element? I have to quantify. Then to get similar heating phenomena using DC input supply, it is called as an alternating current whose RMS value is unknown to me. Hence I say it is a quantity under test. I remove this. Then in this circuit, what I will do? I apply a DC source. Through a DC source, I keep injecting the current through the same resistor which is used for a same duration of time t second. What is that ampere of current I have to inrush to get within the same time duration, same heating effect? Suppose there were it was created 10 joules of heat in the first alternating current approach. 10 joules of heat. To get a 10 joules of heat, when I connect a DC source for a same time t second, what is that ampere I would have inrushed? That amperes I have to calculate. That ampere is defined as RMS value of an alternating. This is called relative logic. The definition of RMS value of an alternating quantity is based on heat produced logic. Then I come to the definition. I just made you clear. Definition of RMS value of an alternating quantity is based on heat produced logic when unknown quantity is applied to a known resistor for a known amount of time. What is the heat produced? I have to take down. To get the same heating effect, when a known voltage source is connected, how much ampere it has to create in the path which will produce the same heat? I have to experiment. When I experiment and get to know so much of ampere, 10, 7, 9, make that heat equality, that ampere is known as RMS value of a first type of AC quantity, which is unknown to me, like that. So let us define it. The RMS value of an alternating current is given by that steady current, that value of DC current, which when flows through a given resistor for a given time produces the same amount of heat as produced by the alternating current when flow through the same resistance for the same amount of time. That was the gist I was telling. The unknown quantity is in the graph. This is the unknown quantity whose RMS value I am likely to define. It should be connected to a known resistor as per the definition. Say R ohm is known. How long you want to connect this? For T duration of seconds. When I connect it, definitely it absorbs power. It absorbs power. It expends it as a heat. How much is that heat produced? I have to quantify by experiment. That is the first part. Then to get similar heating effect, what I should do? I should connect a DC source. That is the meaning. Connect a DC source, inject current inside such that within the same time duration, what is that DC current flowing inside will balance the heat produced in DC applied situation with the amount of heat produced in the unknown quantity applied in stage 1, stage 2, like that. That is the meaning here. See, that I read out, it is indirect definition. The RMS value of an alternating quantity, which I am hovering here. RMS value of an alternating quantity is given by that value of DC current. It is the DC current in connection to the relative definition, which when flows through a given resistance, given means known resistance, for a known amount of time, T second, produce the same heating effect as produced by the alternating current when flow through the same resistance for the same time. So I was making it very clear. Your experiment shall lie in two parts. Apply unknown quantity whose RMS value you want to define to a known resistor for a known amount of time. Quantify the total heat produced. Record it. Then remove the unknown source. In this place, connect a DC source. Inject the current such that within the same time duration earlier what you use, observation T seconds, through the same resistor R. How much current you have to create inside, inject inside, such that heat produced when you apply a DC become equal to the heat produced when you applied alternating current. When heat balance comes in situation, the amperes DC what were flowing inside, that is called as RMS value of an alternating current by number. You have to catch the number. 10 ampere made it possible, 12 ampere made it possible, like that. That magnitude of current DC, magnitude is known as RMS value of an alternating quantity. To do that, what is the experiment you have to do? Consider the waveform as shown to you. It is for T duration. Then cut it into n equal parts. What you can see here, the solid lines show slicing it into n parts. When I make it n part, each width of time become T by N second. Total duration is T seconds. I made the T second into N equal parts, vertical strips. Each strip is having a time duration T by N seconds. Then each strip, you can see a dotted vertical line. That means the dotted vertical lines means the mid ordinate, vertical component of each strip of vertical. So each vertical strip is dotted, which is the component of strip number 1. Second component is strip second. Like that, we call it as mid ordinate, mid vertical component of that. Like I have I1, I2, I3, I4, dot, 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 last number IN. I have n equal parts, n components I will get. So you can see I1, I2, I3. This is the construction we have to do. I1 is the mid component of first strip T by N second. I2 is the mid component of the strip T by N second. Likewise, each strip is having a time duration of T by N second, and each component is I1, I2, I3, IN. This is what is the construction. Then I come to the theoretical aspect. What is theoretical aspect? Such a current I am connecting to a known resistor R for a known time T. Each slice is playing a role for T by N second. Definitely heat is produced in this. I account them. Heat produced during first interval of time slice. It is T by N. Then what is the current flowing? What is the value of current flowing through a resistor? Let's say I1 for a duration of T by N second. Let's call it I1 square R. Current is I1. Mid ordinate of the strip number 1 is I1 square R T by N. What is the length? What is the width for this? T is the total time divided by N strips. T by N joules of heat is produced due to strip number 1. What is the heat produced due to second strip? I2 component of that? I2 square R T by N. Likewise, all the N components, when we connect it to this current as a whole, when I connect, the total heat produced with this resistor with the application of unknown current for a duration of T second mean the accumulated heat produced due to strip 1, strip 2, width, strip 3, 4, 5, 6, 7, N. I am trying to sum it up. So all I1, I2, I3, IN, all these currents, I square R logic, how long they were active? T by N second, T by N second, because they are made equal in width of time. Add up them, that become total heat produced in a total time of T second. That is what you can see here, I1 square T R T by N plus I2 square R T by N. If I add them, what do you find common here? R T N. I find a common. So therefore, what I get here? RT by N. If I take out RT divided by N common, what remain here is I1 square plus I2 square plus I3 square dot 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 plus IN square. You can see here. So RT and N remain common in each term. When I take it out, what remain here is I1 square, add up with the second I2 square, I3 square. This is known as total heat produced with a resistor known for a known time T second when an unknown current alternating is applied. So this is the quantity of heat produced. So what is the definition? RMS value of an alternating quantity is that value of DC current which produces the same heating effect as given AC produces when allowed to flow through the same resistor for the known amount of time. We allowed this unknown current to flow through this for a duration of T seconds. We slice it into N part and we accounted it. This heat must be developed by DC when I apply in the place of AC within the same time T, and what is that current make it possible is the question. Therefore, I know when I connect the DC source here, VDC, and current flowing here is I square RT. I square R capital T R, whatever the total duration T. So that is the total heat produced. When I apply that current for T duration, I square R T is the joules of heat. Therefore, I have here I square RT effective value. I square RT must be equal to the first case study of AC, which is RT by N, I1 square plus I2 square plus dot last number IN square. When I equate it, this must be equal. That is that value of DC current. It is same as that current, that heating effect. So these two must be equated. Hence, effective current square into RT. Whatever is the current which is flowing in the DC application is that current which produces the same heating effect. Then it is called I effective I RMS square RT. I effective or I RMS square R into T with the R resistor for a T duration must be same heat as in the previous split study. That is how I had to equate. When I equate RT cancels. What remains is I effective square equal to I1 square plus I2 square plus IN square, like that. So I'll get all the values in the form of squares and sum. Hope I am audible to you all. Hope I am audible to you all.
Yes,
Hello?
sir.
Yeah, please. So I'll get sum of all the squares of instantaneous values. See how I'm changing my statement. These I1, I2, I3, I4, IN, which I made as mid ordinate of the width of T by N seconds. I call them as a mid components. Mid components, when you touch the waveform, it looks like an instantaneous value, instantaneous value, instantaneous value. Such instantaneous value, when I collectively join, which forms a graphical representation of a quantity. Therefore, these I1, I2, I3, I4, IN are instantaneous values for me. Therefore, sum of squares of instantaneous value remain at the RHS side divided by N. This is called I effective. RT cancels. What remains is I effective square equal to I1 square plus I2 square plus I3 square plus IN square, the last plus IN square divided by N. Then what is I effective or I effect I RMS? So this square, if I take, other side become a root. Here one square I have not taken, just it should be I effective equal to square root of I1 square plus I2 square plus I3 square plus dot the last IN square divided by N. Therefore, so whatever the values you have, I1, I2, I3, I4, IN, they are called as discrete instantaneous values. Sum of squares of them, I1 square, I2 square, I3 square plus the last IN. How many are there? N occurrences. Sum the squares like this way. I1 square, I2 square, I3, last IN. How many were there? N number. Squares, sum of square divided by how many? N under the root, that give you RMS value of an alternating quantity. This is for any periodic wave. It need not be sinusoidal. For sinusoid, we have a shortcut. For any wave, trapezoidal, square, triangular, which is alternating, set of positive, set of negative, if it is having, for such waves, with the help of these instantaneous values, we can calculate it. For that, I'll show one example here. Just see an example. I have obtained RMS and average value of a periodic wave having following values of voltage at equal interval of time. Like voltage is 6.2, 11.8, 16.2. Like this, it is 6.2, 11, 16, 19, 20, 19, 16, 11, 6.2, 0. Some samples were given. Let us say, we will not worry much. These samples were vertical component of voltages. It may be voltage, it may be current. Equation holds good. Then RMS value of this, how I can count? I can take N. What is the N? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many instances are there? 10. N is 10 for you. Therefore, V RMS equal to square root of, okay, sum of squares, 6.2 square. Can you see over here? 11.8 square plus 16.2 square plus 19 square plus 20 square plus 19 square plus 16.2 square, 11.8 square, 6.2 square plus 0 square. What I did here? Sum of all the instantaneous values is squares I did divided by number of occurrences. That's called averaging it, 10, which is inside a square root. That's called as root of first square root. Mean means divided by a certain number. What? Sum of squares. Mean of sum of, that's called RMS. Literally, mathematically, it is matching term. Then take the numerical simplification of this. This stand as 2000 divided by 10 equal to 200 under root, which is 14.14 volt is the RMS value. Likewise, if I see in a domestic house, 240 volt AC, what we call as, in case of single phase in our household, 240 volt AC, single phase. What is a 240? 240 is the RMS value of an alternating wave. We learned alternating wave is having a 50 hertz frequency. 50 hertz frequency means what? So many occurrences, instantaneous values, and the cycles in a second were passing away from our observation. Then it must have a peak, it must have a crest, trough, zero crossing, like that. Increasing, decreasing pattern of wave must be there. Therefore, in that wave fashion, imagine in your mind, there is a certain discrete zero value, 10, 20, 30, 100, 240, like that. Some instantaneous values are riding on the graph. Then those instantaneous values are taken like this. It is for an arbitrary wave. For a sine wave, we need not do this. Shortcut is there. We will see it very soon. For any arbitrary wave, if you have been given instantaneous values, taking this into this fashion, get to the RMS value. I have one more equation here. So RMS value of an alternating quantity given you some voltages like this way. 105, 200, 275, 323, 340, like that up to 0. So we'll see when we solve textbook problem, we'll see some other different way. This is before that. Let make something. I made you to calculate RMS and average value. Average is shown, RMS is not shown. So here RMS is shown in the second example. 6.2, 12, 14.2, 16, 20, 18, 16, 20, 12, 4, 0. Samples were given to you. For this sample of quantities of voltage, obtain RMS value. You can see here. Same thing is being done. Squares of this, add them, divide by number of instances under a root. That stand as your RMS value. This way, whatever we have learned just now, RMS value of an alternating quantity is that value of DC current which produces the same heating effect as the given AC produces when allowed to flow through same resistor for a same amount of time, which is taken by mid-ordinate method, sum of squares of instantaneous values under the root we should take. This is how a work comes for our discussion. So RMS value can be practically viewed from such expression. So next, when we go to another type of representation, average value of a alternating quantity. Before going to do that, suppose the alternating quantity which you are discussing is sinusoidal, because our chapter is sinusoidal waves. What is the method then? Look into this. RMS value of an AC quantity. Suppose alternating quantity is a perfect sine wave like this way, which is having I equal to Im sine theta, 0, peak, half cycle, negative peak, and one complete cycle. If this is the wave, then how we should do? I may consider like this wave, correct? One half of that. This wave is magnified. Then I will slice it. I will have instances, correct? No? Yes, like this I can do. But for me, I need not do heat produced due to I1, I2, I3, I4, I5, In. I need not do it. Definitely, with the help of mathematical relationship, I can do it for sine wave. So how I do for sine wave? The term RMS stands for square root of mean of squares of instantaneous current values. That means IRMS equal to, mathematically, see here, square root of, can you see, under a root, sum of squares. What I do? Integration I do. Integration squares of instantaneous value. How is that? I1, I2, I3, I4, whatever the value if I find on this profile, it is called squares of instantaneous values with whatever the function I have, Im sine theta. Then I have I square d theta. For what duration I will take? 0 to pi only. You can see here, integrate it. Integration means addition of homogeneous quantities for the squares of them. Squares over a period 0 to pi only. Why I am not doing it for 0 to pi? If I take an average of a one sinusoidal wave, this goes 0 because similar set of data you will find in the negative of average goes 0. But in reality, average won't be 0 because it is a periodic progressive wave. Continuously, you will be having a moving wave. Therefore, average is defined for half a cycle. That is the reason 0 to pi is taken. And square of instantaneous value I square d theta. How long of, what is the period of integration for you? Base of integration 0 to pi. You can see 1 by t, 0 to t, f of t. How you write a mathematical form? Same way I am doing. 1 by t means width of integration, duration pi. 0 to t, limits of 0 and peak pi. Square of instantaneous function d theta. So this is mathematical substitution of sinusoidal quantity. I repeat, under a root 1 by pi integration 0 to pi square of instantaneous value d theta. Then I substitute in the I the expression. Can you see here? 1 by pi. What I am doing? I am IRMS. Here I have a square root. I make it a square. Root goes off for a simplicity. IRMS square equal to what? This become open term. 1 by pi, 0 to pi, Im square, sine square, theta, d theta. I am substituting I equal to Im sine theta in this position. I'll be getting this term. So again here Im is a constant. What is a constant? Peak value of a wave. This comes out. This is called Im square divided by pi. Just a minute. Im square divided by pi inside the integration function 0 to pi sine square theta d theta. So you may need to work. How you write sine square theta? 1 minus cos 2 theta by 2, or if you know sine raised to n theta d theta integration directly, you can do it. So I go by parts. So sine square theta is written as 1 minus cos 2 theta divided by 2 and d theta. When I simplify it, 1 by 2 I separate, cos 2 theta by 2 I separate. I can do it. Can see? So 2 is taken outside and 1 d theta minus cos 2 theta integration. I do part by part. When I do, the first term integration goes 1 d theta goes theta. Then with a limit of 0 and pi. Second one, minus cos 2 theta goes integration by sine 2 theta divided by 2. It becomes half sine 2 theta. Again, limits of 0 and pi. You can see here. Outside I have Im square 2 pi. Im square 2 pi. Inside this solution, I have theta from the first term. 1 by 2 sine 2 theta from second term here. Limits of 0 and pi. If I substitute them, I will be able to get the expression. So I substitute first limit. So whatever the pi and 0, 0, this I will be substituting here. When I substitute the limits, I will be getting Im square divided by 2 pi. Can you see here? Im square divided by 2 pi. These terms after simplification result me only pi. Means first term only result pi. Rest get cancelled. Because sine 2 theta, sine of 0 is 0. Sine of 2 pi is also 0. This absolutely goes 0. When you cannot think of the simplification, you can say sine function with the 0 is 0. Sine function with the pi is also 0. Only result is theta. Theta can be pi. Theta can be 0. If it is a pi, pi is the answer. That's all. Very simple. So therefore, when I take a simplification, so pi and pi I cancel. What I get is Im square by 2. So Im square by 2. So this is IRMS square. What is IRMS? I throw the root other side. Square root of Im square by 2 is IRMS. Then if I simplify Im square, I take outside, it become Im by root 2. Im by root 2 or 1 by root 2 is 0.707 peak. This is the RMS value of an alternating quantity. Suppose you have RMS quantity 10 sine 314 theta. Like this way. Peak value you know. If you know the peak value divided by root 2 is your RMS value. No need to do this kind of computation, I1 square, I2 square, no need to do. Directly from the given equation, identify the head of that equation. This is called a peak value. This amplitude, you catch hold of this number, that's called IM. Or in case of voltage wave, VM, catch hold of that. VM or IM, peak value divided by root 2, stand as RMS value. Or in terms of fraction, 0.707, peak value is the RMS value of an alternating quantity. Very simple. You may have a definition in the exam. Define and derive necessary equation for RMS value of an arbitrary quantity. Then you must do this kind of definition and derivation. For any sine wave, it is there, this much only. RMS value and define RMS value and derive an equation for RMS value of a sinusoidally varying quantity. If it is asked, only this short derivation, integration you have to do. Any arbitrary quantity, you have to do this work. So you should be very careful to read the statement of a problem or a question. Any arbitrary, unless sign is mentioned, please do this. If sinusoid is mentioned, please do this much only. So you cannot simply exchange. If you exchange, what will happen? Exam will note that you have not read the question carefully. There will be a partial marks given to you. Therefore, if it is a sinusoidal, you have to do this. Anything simply said, please do this. This is my sincere request. Otherwise, you will lose the marks. So therefore, your effort should not go waste. So therefore, take care of that requirement of a question carefully. So similarly, when I move after the RMS value and definition of any arbitrary quantity or a sinusoidal quantity, we have another representation of a alternating quantity as average value of an alternating quantity. So like RMS, I have another definition, average. What is an average value of an alternating quantity? If we have 10 numbers given to you, 1, 2, 3, 4, like that, 10 counts. What is the average of that mathematically? You add all the 10 numbers, divide by the types, number of occurrences as a 10. You take a mathematical average. Similarly, similar kind of work I will be doing over here. What is that? How I do it? Let us see. So let us say an arbitrary wave is taken like this. Arbitrary wave. It may be like this. Whatever the wave I have taken, this could be the wave. Any arbitrary wave is taken whose average value I want to define. Average value I want to define, then I will connect it to a known conductor. I will not speak of resistor. If I speak resistor, analogous to this resistor, what is the property? Conductance, resistance, conductance. So I will be making use of definition. So whenever I connect under unknown quantity whose average value I want to define to a known conductor and for the known amount of time, then how many coulombs of charges get displaced across a given cross section of a conductor, I am going to calculate. So I'll be using charge balance. Here I use heat balance logic. Heat produced in a first case, heat produced in a DC case, I balanced. In case of average quantity, I'll be using Q balance, charge balance relationship I will be utilizing. Hence, I'll be using similar wave connected to a known conductance or a resistance for a known amount of time. That's what is the definition here. Average value of an alternating quantity. Average value of an alternating quantity is that value of DC current which displaces the same amount of charges across the unit cross section of conductor in given time as would be transferred by the given alternating quantity. Then what is the meaning of this? The meaning of this is, consider a resistor whose property conductor or conductance I consider. So unknown quantity may be like this. Some periodic wave whose clip is taken active for a time duration t seconds. So this duration is sliced into n part, 1, 2, 3, 4, 5, like this way. These are the equal parts, like a first activity what we did. Such a wave is connected to a resistor whose property conductance we will be observing to a conductor for a known time t second. Then in that conductor, what we have to do? Microscopically, we have to think. So I have seen that a conductor connected to a alternating current whose average value I want to define. Mark on that body of the conductor certain unit area and keep observing that unit area. And how long? For a t duration, when unknown quantity is connected to that, how many coulombs of charges pass through that area. When you connect the unknown source for t seconds, we have to count them by number. Practically, for a human being, it is not possible to count them. But the definition is very relative. Very relative. Unknown quantity whose average value we want to define should be connected to a known conductor whose cross section is known to you. Unit area cross section. And you have to keep on watching that area. When you connect a unknown quantity to that conductor, for a known amount of time t second, naturally current will flow in the circuit. When the current will flow, it is a time rate of displacement of charges. How many coulombs of charges practically move from top down or down top, whatever the way you are observing? How many coulombs of charges pass, move away from that window of unit area? You have to count. When you count it, that become a total charges displaced when an unknown quantity is connected. That is a q coulombs, let's say. Then to produce same displacement of charges, what is that DC source I have to connect? DC current I have to inject into the conductor circuit so that within the same time of duration, q coulomb must dispense. What is that ampere make it possible? If it makes a capital I current, I is known as average value of an alternating quantity. That is a relative definition. So for that, what I will do? I will analyze this in a split, considering the sinusoidal wave fashion or any arbitrary wave fashion as shown in the case study here. Similarly, I just take it. Then I just make it equal n parts. Each component is I1, I2, I3. Same thing what we have done. Then I know that what is the charge displaced by current I1 in t by n second, I will quantify. So Q equal to I into T logic. Coulomb of charge equal to I into T, or current is Q by I, Q by T. Time ratio Q by T. It is called as displacement of charge with the time. Q by T stand as a current. What I will do? What is Q? Q is I into T. What I will be doing now, for the unknown current having n equal parts, for each part playing t by n seconds, I will be quantifying the coulombs of charge displaced by I1 current in t by n second is called as Q1 equal to I1 t by n. Q2 for a second displacement, second strip of current, Q2 equal to I2 into t by n. And so on the last strip, In, it is Qn, coulombs of charges Qn equal to In into t by n. So each strip of width of time having I1, I2, I3 currents in each displace respectively Q1 charges, Q2 coulombs, Q3, Q4, Q5, Qn. If I consider whole together at a time, total charges displaced become addition of Q1, Q2, Q3. That's being done. The total charges displaced by the unknown quantity in t seconds over the known conductor, I can add them. Let's see here. I1 t by n plus I2 t by n. Remember Q1 plus Q2 plus Q3 plus Qn, like that. It is the addition of all the terms 1 plus 1 plus 1 plus, like that. That is called unknown quantity connected to a known conductor. The total charges displaced across the known cross section of conductor is Q by this equation. But definition says average value of an alternating quantity is DC current, that value of DC current which displaces the same amount of charges. So what is that DC current on whose injection into the conductor balance the Q of this with the case study number 2. Therefore, as per the definition, Q is the total charges displaced by an unknown quantity alternating. This has to become balanced, which should be equal to I average into T. I is the DC current. How long? T. If I multiply I into T, value of coulomb of charges must be equal to total sum I have done. This is as per the definition. Average value of an alternating current is that value of DC current which displaces the same amount of charges. This is the amount of charge displaced by unknown quantity in T seconds. In that same T second, what is the DC current? If I multiply, quantify the same amount, it is I average into T. When these two must be equal, I have this I average into T must be equal to T. When I equate here, T is common, T is common, T is common, T cancels out. When T cancel, what remains is I1 plus I2 plus I3 plus IN divided by N. So average value of any arbitrary alternating quantity is sum of the instantaneous values divided by number of instances. If there are N occurrences, I1 plus I2 plus IN divided by N. This is just like a mathematical average. 10 numbers are there. Average of 10 number, how do you do? Add all 10 number, divide by times how many it has appeared. Total counts of physical occurrences, 10. Like how that. So this is how definition goes. So for that, I just took an example. Average value of an alternating quantity, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 instances. Values are V1, V2, V3. Instead of current, these are the voltages. V1, V2, V3. Can you see here? Directly they are dragged and dropped here. Add them in the numerator, divided by 10. That gives you the average value of an alternating quantity. So RMS is one type, average is another form of representation. Average value is always a DC representation. So DC content is a average by value. So therefore, average value of an alternating quantity by discrete instances given to you is just an average of instantaneous values. So similarly, you can see here average value of this expression, this quantity 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, 10 values are picked here. Add all 10 divided by 10. This give you average value. This way you need to check yourself how average value of an alternating quantity can be computed. This is called any arbitrary alternating. If it is a sinusoidal, I have a direct equation like Im by root 2. In case of RMS, I had. For average also, I have a direct equation. What is that? We will see. So this is with respect to any arbitrary wave having sliced it into n part. Time of each is t by n, playing to displace q1, q2, q3 coulombs of charges. Total displaced charges is quantified. To get the same displacement, what is that DC current? Make it possible. This way, our average value of an alternating quantity is that value of DC current which displaces the same amount of charges across the given cross section of the conductor in given time. So this way, a short note of derivation comes. You may have a 6 or 8 marks question. Define and derive the equations of average and RMS values of a quantity. Then it is both you have to do. For a sinusoidal only sinusoidal part you have to do. So for sinusoidal, what we do? Average value of a quantity, which is sinusoidal, perfectly sine wave. If I say it is like average value of a sinusoidal quantity, like Im sine theta. Whatever the wave I have taken here, I have taken Im sine theta. What is the average value of that? Average is defined for half a cycle. So therefore, it is taken like this way. So I can define 1 by pi 0 to pi I d theta. So when I substitute for 0 to pi, I'll be getting integration of sine as minus cos, limit of 0 and pi. When I make it out, this become 2 Im by pi or 0.637 Im. So it means to say average value won't be 0, it will be somewhere a particular fraction. So earlier what we have seen is RMS value. RMS value of alternating quantity was Im by root 2. So somebody may ask, sir, what happens if I take a complete integration? You are going to get, that is nothing but Im by 1 by 2 pi, 0 to 2 pi. If you integrate, you will reach the same answer. For RMS, I'm speaking. For RMS value, I have taken half a cycle. If I take a complete cycle, what will happen? IRMS equal to root of 1 by 2 pi, 0 to 2 pi, I square sine I square d theta. It will reach the same answer. You can try that. Hence, it is easy to say half cycle. But average, I have to take half only. That's the reason average is taken for half. 1 by t, 0 to t, f of t integration like this way. So when I take this integration, Im comes out, divided by pi, sine theta integration goes to cos theta. Limit of pi and 0, it makes it 2. Pi also turns -1 and this also turns 1. So therefore it become total 2 in the numerator, 2 Im by pi, or it is 0.637 Im. So by this way, we got to know RMS value, average value of a sinusoidal quantity as well as any other arbitrary wave. Last two definition in the end of the page you have. What is form factor? Form factor is the ratio of RMS value to average value, whether it is a current by current, voltage by voltage. It is just a ratio. What kind of ratio? RMS value of a quantity which you are taking to the average value of a quantity. If you take a ratio, that is called as form factor of a representation. Another factor we have peak factor. It is the ratio of the peak value appearing in the wave. That is called as a peak to RMS value of the wave. When I take a ratio, that is called as peak factor. So this way we come to the basic introduction to the waveform terminologies and comparison of quantities by RMS and average like this. Okay. So now we will stop here. In the next class, we go ahead with discussion of further quantities like what we mean by waveform, phase difference. Lot of things are there. We have to learn these things in the coming sessions. Meantime, today we have learned RMS value of an arbitrary quantity, RMS value of an sine wave, average value of a arbitrary quantity, average value of a sine quantity, and two